Right. In this video, we're going to look at waveforms. We're going to look at the acoustic property of amplitude. So we're not going to have any more formulas connecting to period and frequency and wavelength and all of that, but we will have some formulas here. There's going to be some math. It's going to look a bit scary, but you don't need to worry about that. Mainly, I just want you to understand some of the relationships there. But let's start with uh, this basic waveform that we were looking at in previous videos. So here's a simple waveform, just sort of increasing and decreasing pressure over time. Notice the axes marked here. And now with amplitude, the basic thing we're interested in is displacement. So at any point in time, the amplitude is displaced some amount from that zero line. It can be displaced by zero when the line is actually crossing the zero line, the pressure is crossing zero. It can be positive, it can be negative. And mostly what we're interested in is displacement at the maximum and minimum, so the greatest pressure and the lowest pressure. And generally, when we're talking about the amplitude of a simple wave, what we mean is the displacement from the zero line to a maximum. We can also talk about peak-to-peak amplitude, which is just the distance between the maximum and the minimum. Now, for a simple wave, this is exactly twice the basic amplitude, but there are other more complex waves where the maximum, the distance up from the zero line to the maximum is not the same as the distance from the zero line down to the minimum, so the peak-to-peak amplitude isn't exactly twice the amplitude. We don't need to worry too much about those distinctions in general, but it's worth being aware of them. Now, here's some math. Now, before we get too deep into that, the basic measure of amplitude, as we've said, is pressure. And in the metric system, the basic unit of pressure is a Pascal. But we're all familiar with measures of how loud a sound is. And in a little bit, we're going to learn about why we don't use loudness here. Loudness to a phonetician is actually a perceptual measure, not an objective acoustic measure. So there we go. We don't have to wait for that. But we'll get into that in more detail later in the term. But we're used to thinking about amplitude or experiencing it in terms of decibel. Now, a decibel is an interesting kind of measure. Mathematically, it's actually a unit-free measure. A decibel is a logarithmically scaled ratio. What does that mean? You don't technically need to know that, but I think the math of this is actually kind of beautiful. I mean, I know it's beautiful. I hope that you can come to appreciate a little bit. We're going to look at some formulas. You don't need to be able to do the math. It'd be good to be able to type it out. I've got a link to a scientific calculator in the description of this video for you to play around with some of the things that we're going to see here if you'd like to. But the main thing I want you to come away with is the relationships that come out of this. Okay, so let's have a look at that. Here are those formulas again. So this is out of the textbook. A couple of ways to get a decibel measure of amplitude out of the pressure measures. So on the left we have amplitude in decibels, and on the right we have some amplitude measures in pressure. So A here is the pressure measure that you're using, and A0 is a reference measure. And from the textbook, you'll know the reference is often a threshold of hearing. Sometimes the reference is the smallest unit that can be measured if you're dealing with a digital signal that hasn't been calibrated for Pascal measures of pressure or something like that. And sometimes it's the maximum that can be represented. And we sometimes talk about amplitudes differently depending on what the reference is that we're using. You notice there's two different formulas here. That's because pressure and energy have a particular mathematical relationship to each other. So the same wave, if you're measuring amplitude in terms of energy versus pressure, these formulas should give you the same amplitude for the same wave. It's just what are you measuring it in terms of energy amplitude or pressure amplitude. Again, you don't need to worry too much about that for our purposes. Now here's a couple of thoughts about logarithms. So you'll notice with that formula, it's based on a logarithmic scaling of this ratio here. Now, in normal measurements, pascals, seconds, whatever, uh, when you multiply something in a normal measure, once you transform that into a logarithm, what you're doing is you're adding. So for example, if you multiply by 2, that's about a 6 decibel increase. So this is something that kind of does people's minds in sometimes. The difference between an amplitude of, say, 1 and 2, that's a doubling, that's a 6 decibel increase. The difference between an amplitude of 100 and 200, that's a doubling, that's also a 6 decibel increase. Right? So what logarithm does is, as the numbers get much, much bigger, the logarithmic distances stay the same. Right? You scale things up and the logarithms stay manageable. And if you remember from the textbook, it talks about how we can perceive these tiny, tiny differences in amplitude, and we can also perceive really large differences in amplitude. And so what logarithms do is they allow us to handle those and those with the same scale. And that seems to be how our hearing system works. So although decibels are a measure of the acoustic properties of the sound out in the world, they translate nicely to how we perceive sounds, and they connect smoothly with that, and that's kind of convenient. So the other thing that we see in this table is exponential. So if you square a value, you take the 10 and you square it, getting 100. That's a multiplication in logarithm. So squaring is a multiply by 2. So if the pressure is squared, the logarithm of the pressure is doubled. And that's actually what we see here, right? Energy is basically pressure squared. And so we just double the factor that goes out there. Okay, so that's some properties of logarithms, and we're gonna see how that plays out in a minute here, because we are going to be looking at amplitude in terms of decibels, and it is important to know how decibels work differently from other measures because of this logarithmic. Uh, so here's a graph of a couple of waves, and I'm using what we often find in programs like Pratt and Audacity and other sound programs. We don't have pressure measured in pascals because and it's important to remember, the microphone that you have on your phone, on your laptop, if you have an external microphone, it's not calibrated to say this is X X number of pascals. It's just giving you, well, this feels like a lot, this feels like not much. And there's the maximum that it can record and the minimum that it can record. And so often what you see is something like this, where the maximum is just set at 1 and the minimum is just set at -1. It's just an arbitrary reference. But so we'll use that sort of unitless measure of amplitude. And we see the black wave, which we're calling a wave 1, its amplitude is 1, right? From the zero line up to its peak is 1. So its amplitude is 1 arbitrary unit. And the red wave, it's only half as high. Its peak is at 0.5. Okay? So if we're going to go and use this pressure, we're looking at pressure right now, so we're using the pressure formula that has a coefficient of 10. And let's calculate the amplitude for those two waves. So for the wave 1, what reference can we use? With something like this, we'll use just 1 as a reference. So that's the maximum that it can be. And wave 1 has an amplitude of 1. So logarithm of 1 over 1 is 0. Multiplied by 10, we get 0 decibels. And this is sound pressure level because we are kind of going by pressure. And wave 2, the amplitude is 0.5. And when we calculate this out, the logarithm of a number between 0 and 1 is negative. So we get, and then multiplied by 10, we get negative 3.01. So one thing that I want you to pay attention to here, the difference between these, wave 1 is 3.01 decibels higher than wave 2 in terms of its amplitude. 3.01 decibels. Now, what if we take some values that are more likely to be encountered in something like speech? So we have amplitude 1 is 52 millipascals, amplitude 2 is 26 millipascals. And we're going to have a bit of fun here. I'm actually going to relate that to micropascals, because one of the ways that we can measure amplitude or use as a reference is the threshold of hearing. So the threshold of hearing is around 20 micropascals. There are 1,000 micropascals in a millipascal, so wave 1 has an amplitude pressure of 52,000 micropascals, and wave 2 has an amplitude of 26,000 micropascals. So if we do this math, we get 34.15 and 31.14 decibels. Different numbers than we had before, but the difference is 3.01 decibels. So what's going on here? Decibels basically boil down to ratios. So if one wave is has twice the pressure of another wave in terms of amplitude, then it's going to be, no matter what the absolute value is, but whether they're both really quiet and one is twice as loud, or both really loud and one just happens to be twice as loud as the other one, they're still going to have a difference of 3.01 decibels. And in fact, there's one more trick, and I understand that I may have already lost you in this math. One more trick. What if we just use a direct comparison between wave 1 and wave 2? The math of this works out to exactly 3.01 decibels. So I don't know. I mean, to me, this is a wildly beautiful thing that we can do. We can take this thing that would be quite unwieldy if we were just looking at pascals, where we're dealing with micropascals in some cases, and millipascals, and maybe even tenths of a pascal at the other end for really loud sounds. And it boils down. We can boil it down to we're only dealing with decibels, tens of decibels, that kind of range in terms of the differences in sound level. If people are shouting, if people are whispering, if people are talking normally, we still have a kind of manageable, kind of humane range of values to deal with, and we can compare things easily. So I know the math of logarithms can seem overwhelming, but it is this really useful mathematical trick that gives us a manageable measure out of what could easily become unmanageable measures. And along the way, I've mentioned that our recording devices aren't always calibrated to an exact pressure. Because logarithms deal with ratios, we always have a meaningful way of comparing them, even if we don't have an absolute calibration of pressure. Okay, so let's see, what do we have? Just to sum up for this video, I've been going on a lot here. Amplitude, right? So there are ways to convert between pascals, the sort of raw pressure measure, and decibels, which is the more common way of representing amplitudes. There are very good reasons, perceptually, mathematically, to use decibels rather than raw pressure measures, and it's more convenient. Just have to do a little bit of math. You don't necessarily have to do this math. I think it's important to understand at least the relationships here. What is it that logarithms are buying us? There's a lot of terms in this section: pressure, energy, intensity. Really, the main thing that I want you to come away with is the idea of logarithms. Understand that whether we're measuring amplitude in terms of pressure versus energy, we're going to get a slightly different formula. It's going to have the same basic structure to it, though, and that, I think, is good. That's the main takeaways. Do read through the textbook for this section, because it goes in slightly different, focuses on different aspects of this that are worth looking at. And in the next video, we will look at phase.